Good morning, students. So, students, today we are starting semiconductor and its devices, right? A new type of thing, new topic, new type of thing. We have not studied anything like this before. Okay, entirely different type of physics, which actually in engineering, which we study in electronics. Okay, electronics and telecommunication, electronics and instrumentation. There we study more about semiconductors, right? And so far, we didn't talk about it. Okay, so far we never talked about it. That we have studied in entire 2 years, 11th and 12th. There was no connection with semiconductors so far. Okay, let's see what it is. Semiconductors. Okay, now as the name suggests that semiconductors, that means they are not in conductors, they are neither conductors nor insulators. They are in between. Okay, conductors, semiconductors and insulator. Three types of elements we can say we have: conductors, semiconductors and insulators, right? If we have to get the difference between them or differentiate them, what we can say normally, whatever we have studied so far, we say that conductors are there, the conductivity must be very high. Conductivity is high and resistivity is low. Okay, resistivity is low. Insulator, what you will say? Conductivity is very less, right? Resistivity is very high. Conductivity, in fact, conductivity is not there in insulators. Conductivity is not there. Conductivity is almost zero. It's almost zero. But can we make them to conduct? Yes, with the help of temperature, with the help of voltage difference, we can conduct electricity through insulators also. But if suppose we are talking in terms of the temperature at which we are not excited the electrons, and that one we can say its conductivity is almost zero. Okay, resistivity is very high. Resistivity is very high. Fine. Now, semiconductors means what? Conductivity is less than conductor and resistivity is higher than conductor. Okay, but resistivity is not this much. Okay, so conductivity, this chapter we are studying. So here we have semiconductors. So conductivity is less than conductor. Conductivity is less than conductor and resistivity is higher than conductor. Okay, so this is how we can differentiate at the moment. But now the question comes or question arises when we have conductors, they are pioneer in conduction, and we have insulators, they are pioneers in insulating an object. Then why we require this semiconductors? What is the need? Correct or not? What is the need? They are neither toppers nor the backbenches. They are in between. So who requires them? At the moment, whatever researches, maximum researches which are going on. Okay, maximum inventions are happening. They are happening in semiconductors. Okay, till now we were importing them, and because of the shortage of semiconductors, we were knowing that till last year, maybe in this year also, till July or June, there was long waiting for cars. Cars also semiconductors are there. Where all semiconductors are we using? In everywhere around us right now. Every sensor, okay, whatever sensors we have, they are all based on semiconductors. LED, that means light, that is all based on semiconductor devices. Solar panels, okay, we are getting the electricity from solar panels. Now, many people are using solar panels at their home. So again, semiconductors. TVs, now TVs are LED TVs. So television, laptops, computers, mobiles, robots, okay, everything is using semiconductors. So whatever advancements are happening, okay, whatever inventions are happening at the moment, all are happening in this. So it's very, very important. Right. But the question again arises, they are neither toppers nor in the backbencher seat. And what is so important about these semiconductors? Okay, we'll discuss it. First note this. Done? Yes, sir. Okay. So the question is why semiconductors are important, right? Why semiconductors are important. Okay. Why semiconductors became important? Now semiconductors are such that you can convert them into conductor also, and you can make them as insulator also. That means you can control their conductivity. Okay, depending on our requirement, because our requirement is there. Sometimes we want current to be there, sometimes we don't want current to be there. Semiconductors gives that flexibility to us. When you have a conductor, that flexibility is not there. Okay, so they gave us the flexibility that we can convert them into conductor and insulator. Second, we can easily control the number of charge carriers in it. Charge carriers means the value of current. Charge carriers means electrons. Normally, conductors, when we talk, who carries the energy? Charge. Okay. So, how much charge we want to flow? Okay. How much current we want to flow? That we can control very easily through semiconductors. And third, the direction. Like in conductors, if suppose I have a conducting wire, okay, if I apply the potential difference like this, what will happen? Current will flow like this. But if I do an opposite way, the current will flow in opposite direction. Okay, but in semiconductors, we can control the direction of flow also. Maybe in this way it should flow, in this way it should not. Okay, that all can be done very easily in semiconductors. In conductors, not possible. Okay, that's why these semiconductors became so important. And the biggest of all, the size. Size is very, very small. Okay, size is very, very small. So that's why all the chips, okay, have become very, very smaller now. Earlier days, it was very big. Okay, they were very, very big. So now you can see that you have mobile is so small. In that mobile itself, you have chips inside. Their size is very small. Okay, there is motherboard inside. You see that how small it is. And in that one, all the instruments are there. All the elements are there, which are there in the bigger motherboards also. Right, that is all because of semiconductors. Okay, so what are the plus? We discussed which answer we are writing, why they are important. One, we can control the flow of current. Flow of current can be controlled easily through semiconductors. Okay, second one, the direction of flow. Okay, the direction of flow the direction of flow can be controlled. Okay, these are the most important properties of semiconductor which were not there in conductors and insulators. Okay, now in this one itself, that also point is there that whenever you want, you make it as a conductor. Whenever you want, you can make it as a insulator also. That means you don't allow it. That doesn't mean that it will become insulator. That means you don't allow the current to flow through that. Okay. So flow of current can be controlled as well as the direction can be controlled. Note this one. Done? Okay. So the question is, before semiconductors, which is somewhere around 1930s, between 20 and 30, okay, the semiconductors were found. And some experiments started happening after that. Okay. So before that, or before actually the semiconductors came into these electronic circuits, before that we were not having anything like that, which can control the flow of current and which can control the direction of current. Were there. We were having vacuum tubes. Okay. Before semiconductors, we were doing it. It's not that it was not there. Whatever were the limited things available to us, we were doing it. And those things were called as vacuum tubes before semiconductors. So vacuum tubes were there. What were vacuum tubes? Vacuum tubes is obviously vacuum. Suppose this is a glass tube, vacuum is there in that one. Okay, in this one what we did, we made one anode over here. This is anode and here is cathode. Okay, this is cathode and this is anode. Now what? Very similar to photoelectric effect, because we want current. In photoelectric effect also we were getting current, but in photoelectric effect what we saw? We saw that we were making the photons to be incident on the metal plate, and metal plate was making electrons, rather electrons were ejected from metal plate, and then because of the potential difference of light we were getting the current. Exactly same thing in this, but in this one it's not photoelectric, it is thermionic emission. That means here will be one heater, and this heater you will be heating. Okay, like this. So what will happen then? Electrons will come out over here. So electrons will come. And since this is anode, you have made a battery, you have connected across. So all the electrons will go in this direction. We know that. Okay. So these electrons will go in this direction. That means current will come in this direction. Is it possible for current to go other way? Not possible. Current can come in this direction. Okay. So this way we were controlling the direction of flow of current or direction of flow of charge. Okay. One property we have covered up. Second one, we can control these electrons also. The number of electrons which are going to move from here to here, that also we can control depending on how much energy are we giving. Right or not? How much energy are we giving? Depending on that, we can control the flow of charge also. Exactly the same property that we saw in semiconductors. They can control the flow, they can control the direction. Both we were doing with this vacuum tubes. Okay. So then suddenly why semiconductor everywhere? We were doing it before also. Then what is the problem? There are many disadvantages in this. There were many disadvantages. Okay, what were disadvantages? See, disadvantage were first is size, big size. Okay, as compared to semiconductor, so big size. That's why earlier days these TVs were very heavy because inside were these vacuum tubes, very heavy TVs, and box used to be there, very big box. Nowadays you see how small TVs will be, thin TVs are coming. That's because of semiconductors. Size is very small, right? So here size is big. Second, vacuum is to be created. Now, creating vacuum is not easy. Okay, vacuum you have to create. Why vacuum need to be created? Vacuum need to be created because if air molecules are there, these electrons are going to collide with air molecules. Okay, so their speed will be decreasing. So they can vary the current which is there inside. So that's why we want vacuum. Okay, to create vacuum is a big task. It's tough work. Okay, creating vacuum is difficult. Okay. Third, response time. They require response time. That means not like that you switch on the TV and immediately you, right? But earlier days it takes time. Some response time. The lagging is there. Time lag is there in these vacuum tubes. Okay. Time lag in function. Okay. Fourth, they used to, what to say, when you use them for some time, then there are chances that they will become non-functional. And just like bulb is there, our olden bulb, what happens? After some time it get fused. So they also get fused. Okay, their life is small. Vacuum tubes, life is smaller. That only I am writing. Okay. So vacuum tube, life is small. Okay, non-reliable, right? They do not operate on low voltage. If suppose low voltage is there at home, your TV, you cannot switch it on. But now it works even at low voltage. Okay. So first is reliability. They are not reliable. Reliability is less. Sixth point, cannot function at low voltage. Okay. So we were doing definitely the functions which semiconductor is giving us, but the device that we were using was having many disadvantages. So we were not happy. We were searching something. And then suddenly semiconductor came and we changed everything. Okay. So then advantages of semiconductor what? Size small. Okay. No vacuum creating is required. No time lag. Okay. uh, semiconductors life reliable. Okay, their life is very big. Okay, very large. Reliability is more and does function at low voltage. Okay, so first write disadvantages of this vacuum tubes. At the same time, then write advantages also of semiconductor. Okay, note it. Done. Okay. Now this vacuum tube that I have made, that is what actually these are diodes. This is diode. Two electrodes are there. These are called diode. And how will be semiconductor diode? Semiconductor diode is very small. It's very, very small. Like this. Okay. Like this it will be. And here will be two legs of these. This is diode. Okay. This is diode. This is the size. Whereas these tubes used to be of this much size. This is diode and triode. Okay. So it makes the size also small. Thickness is also not there. Whereas they were having thickness also. They were bulbs basically. Okay, they were bulbs. They were like this. This was the shape. Like this is cylindrical, and then here it will go in this way, and then come here, and here it will be like this. Here will be, okay, here will be your cathode, and here will be anode. Like this it used to be. Big in size. This is very less. Okay. All right. So let's move ahead. So vacuum tubes also we saw. Semiconductor we compared. Right. So now, if you want to understand semiconductors more, their operations more, then we need to discuss about the energy. Okay, bands, energy bands in semiconductors. Okay, let's write energy bands in semiconductors. Semiconductors you don't write, write in crystal. Energy bands in crystal. Right? So when we talk about energy band means, or rather energy also. Energy is basically of electron which is orbiting around the nucleus. Okay. Basic structure of any element is what? Atom. Right. So energy, when we are talking, energy here is energy of electron orbiting around nucleus. Okay. We have all studied atom. So we all know that what is the energy of electron. At least in hydrogen atom we have the idea. Or hydrogen like atoms we have idea. So let's focus on that itself. Okay. So when we talk about an isolated atom, We studied isolated atom. Okay. In Bohr's theory, we studied isolated atom only. So when we are talking about isolated atom, we know that in ground state, electron will have what energy? Ground state, it's a 13.6 eV. Okay, then we come first excited state. First excited state. And this one energy was minus 3.4 eV. Then comes second excited state. See, the difference is decreasing. Okay, difference has to decrease. So minus 3.4 eV, here is minus 1.51 eV. And then this is minus 0.85 eV. Like this we saw, right? First excited state, second excited state, and third excited state. Okay. So this energy levels were fixed energy levels, confined. That electron will be in this energy level only when it is in the ground state. When it is in the first excited state, energy level will be this only. It will not have any variation. Here also it will have this and it will have this. So this is true. Okay. Energy levels of electron are fixed in isolated atom. It's fixed. Okay, there is no variation at all. But when we talk about crystal, in crystal it is entirely different. Right? What is crystal? Crystal means is when there are many atoms, okay, together. When there are many atoms together. Maybe suppose if I try to make it, okay, let's take one, this is your nucleus here, this is first orbit here, second orbit, third orbit. Okay. In this one, an electron is here. Let's assume this electron. One electron only I am talking. Okay. Now what? There is one more atom nearby, very near. So one more atom nearby, that means if I can, it's possible, let's see. Yeah. Something like this. Okay, very close. Now in this one, this electron is bound with this nucleus or this nucleus also? This nucleus only is attracting this one or this is also attracting this one? This is also attracting. Right or not? Still, I have shown you the gap. This is a huge gap. Huge gap it is. When I am talking about a crystal, okay, when we are talking about a crystal, then we know that we are talking about 1 mole of a substance. When we are talking about 1 mole of a substance, that means there are 6 into 10 to the power 23 atoms. 6 into 10 to the power 23 atoms. The very high density. So it's not isolated atom more. Now it's a crystal. So in a crystal, every atom is surrounded by infinite number of atoms. So one electron is not confined to one nucleus. Okay, it is influenced by all others surrounding it. So because of that, what happens? The outermost electron, not outermost, higher energy electrons, because lower, that is ground state will not have much interaction. Okay, ground state, if I say that 2 electrons are there, they will not have much of the interaction. They are closely knit with their own nucleus. Okay, they are knit with that. But the higher energy, maybe first excited state, maybe the second excited state, third excited state, whatever the highermost excited state, they will be associated with all the atoms around them. Okay, they will be associated with all the atoms, right? So because of that, what will happen? The energy energy of electron. No more be fixed. Here what? Fixed, isolated atom, fixed energy. But now there is no fixed energy. Okay, because every electron is associated with all the atoms around it. Okay, every electron which is in the higher excited state is associated with all the atoms around, because the space is very less. Okay, because of the huge density. Okay, space is very less. So, because of that, what happens? Every electron is having specific energy. What does that mean? That means in this atom, this electron that I have shown, first of all, this is a crystal of the same element. Okay, so every element will have electrons in the same orbits, right? So electrons, suppose this is the highermost orbit of this atom and this is the highermost of this atom, still both electrons will have different energy. They will not have same energy. Okay, every electron in the orbits of the atom will have different energy, unique energy. Okay, what happens in crystal? In crystal, every atom is unique atom. That means the other atom cannot be like this atom. Every atom, maybe if suppose we are talking about 6 into 10 to the power 23 atoms only, every atom in this one is unique atom. Every electron in this is unique electron. And every electron's energy is unique energy. Unique energy means you will not find the second electron which will have the same energy. Okay. So first point, every atom is unique atom. Right? Second, every electron is unique electron. Energy of each electron is unique. You can ask that how it is, because it's in the highermost orbit, and highermost orbit of every atom is, because same atoms. So how can it be different? It depends on the spacing. If suppose that we make 10 atoms, I am going to make. Okay, suppose this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I made them in line. Suppose in line only we'll try to understand that. Okay, so we'll take this atom. Suppose these two atoms I am taking. So when I am taking this atom's electron says what? I am surrounded by 4 atoms on the left and 5 on the right. Fine, good. So on the left side, it will have association with 4 atoms, that means 4 nucleus, and it will have also association with electrons of this. Okay, it's not that only atom is going to influence it, electrons also influence. Same way, this one is saying that there are 5 atoms on right of it. Perfect. When you talk about this second one, what it says? It says on the right side it has 4 atoms and on the left it is 5 atoms. So how can both be same? Are they same? No. Are unique. Same way 6 into 10 to the power 23 atoms are there, very close to each other. And electron in every orbit of them has unique energy. Okay. That is the difference between isolated atom and crystal. Is it clear, students? What second part? I'm not getting. Every electron is? I said to you. I said already about atom, right? An electron which is there in this atom is not the same about this one. Because this electron which is here is influenced by 5 atoms on the left and 4 on the right. Is there anyone like that in this? You are not understanding. Electron in this is influenced by 5 atoms on the right and 4 on the left. Is there any electron other than this is influenced by same number of atoms? Then it's unique only, no? Every electron in this one is having unique energy, unique position, depending on the atoms. No atom in this one can say that I am having same type of specification like this one. None. Everybody is unique. And since everyone is unique, electrons are unique. And every electron is having specific energy. Okay. Now the question is, if I suppose, first you note this, okay. First you note this, both. If you want to have anything from here, you can note, and then I'll change the slide and then we'll go ahead. Okay. Come on, do that fast. Done? Shall I change the slide? Okay. Complete. Completed, students?
Yes,
Okay. So now we have talked over here which electrons higher energy state, that means excited state. Ground state we are not talking. Ground state more or less, not more or less, it will have fixed energy only. Minus 13.6 eV, if you are taking hydrogen, it will be minus 13.6. But if you talk about others, like let's say which one we have taken at the top over here, the minus 0.85. Oh, so minus 0.85. We have talked about this, the highest energy. So what happens? There are how many atoms? 6 into 10 to the power 23 atoms. Okay. So 6 into 10 to the power 23 atoms, if suppose we are talking about single electron in that, I'm talking about single electron. So how many energy levels I'll be getting? Every electron is unique, every electron is having unique energy. 6 into 10 to the power 23. That many for a single electron itself. Yes. Okay. So, this minus 0.85 that energy we have, when we are going to talk about the crystal, if I am going to make that energy minus 0.85, what will be the energy? We are saying everyone is having different energy. So, if one of is having minus 0.85, another will not have minus 0.85, its energy will be something else. Okay. So, are we going to get this particular energy level? Answer is no. Then you will be getting 6 into 10 to the power 23 energies will be there in very, very small gap. Okay. So, in that one, fixed energy will not be there. So, what will happen? Just try and understand this, okay? And if any doubt is there, ask me. Alright. So, what I am doing here, minus 0.85 energy level that was there, correspondingly I am making the energy in crystal. Okay. Now, the question is, when you have that many atoms which are associated with a single electron, okay, so energy level or energy value is going to be more than minus 0.85 or less? Answer is both. Energy will be more also and energy will be less also, but very small, minutely. Not that minus 0.85, so next will be minus 0.82, minus 0.79, nothing like that. It will be well within the boundaries. The variation, the range will be less only. Okay. So what happens? Till now minus 0.85 I was having like this. But now it will be slightly above also. The same electron I am talking about, it's not a different electron, okay. Same electron. Okay. Which state it is? I think this is third excited state. Okay. So third excited state electron only I am talking. Its energy, the topmost energy will be here and the lowermost energy. And between this, how many are there? 6 into 10 to the power 23. So it will be like this. Still I have made, okay, more. Okay. 6 into 10 to the power 23 means how much? You know that, right? It's like this. So does it hold anything to say that only minus 0.85 electron volt is the energy? That discrete energy levels disappears when we talk about crystal, and their place is taken by energy band. We call this as energy band. This is energy band. Okay, because reason is there is no discrete level, like minus 13.6 eV was there when the straight line was there. But here no more straight line. It's a group, it's a bunch. And I cannot identify only minus 0.85 because they are all same electrons which are in third excited state. Okay, so what is the energy they possess? They possess the energy in a band, and the difference between them is negligible, very, very small. Okay, this energy gap, if you say that the difference between this and this is also very, very less. It's not that it's a huge gap, that's what I told you. Okay, so energy level thing is not there in crystal. Then its place is taken by energy band. Okay, in crystal, energy level found in isolated atom has no significance. Its place is taken by energy band. Okay. So third excited state I made, in the same way second excited state will be there, first excited state will be there. But Second excited state level, the width will be less. Okay. First excited state even more less. And ground state, we can say that it's almost fixed. Okay. So if suppose I make the lower one, okay, this was third excited state, right? Third excited. The second excited state, if I make, okay, or slightly bigger shall I make, because first excited state also, okay, fine, we'll make. Okay, then we'll fill it. Comparatively less interactions are there. That's what I'm trying to show. Okay. More you go up from the nucleus, more you are having interaction with all the atoms. Less energy is there, your interactions are with less. Okay, less atoms, less electrons. Okay, this is second excited state. Then you'll have first excited state even more smaller. Okay, like this. Then we can fill this one also. And then final is this. So normally we will not make ground state at all. Okay, we'll start with the first band only. So say first excited state, and this is ground. Okay, so in crystal we don't talk about energy levels, we talk about energy bands. That theory I told you right now. Is it clear?
Yes, sir.
Note it. Completed? Okay. So let's make them energy bands. How we are making something like this. And this will be ground state. They will be making like first band. Okay. Then you'll have second band. Slightly bigger. Okay. Then third one. Gap I have given too much here. Okay. Okay. So you decrease the gap. Then third one. Third band is here. Highest band, let's say. This is the highest band. So highest band we call as valence band. Okay, highest energy band is valence band. Is there anything above that? Yes. Above this is conduction band. Conduction means where conduction electron used to be there. We used to say, no, in a conductor, what is there? Electrons are free. They are on the surface. They are ready to conduct, ready to move. Right? As we applied electric field, they start moving and we get current. Okay, so here also, when you want, now I am at crystal at the moment. Let's assume that I have gone into semiconductors. Okay. So here also, if you want them to conduct the current, you want conduction electrons. So electron need to be in conduction band. So above valence band is what? Conduction band. This is conduction band. So in conductors, now here we are talking about crystal. I never talked about this as semiconductor or insulator or conductor. That means it's true for all. Okay. So in conductors, there are electrons readily available in conduction band. Readily available. At 0 Kelvin also. Okay. 0 Kelvin means you are not giving any thermal agitation to them. Okay. No energy is being given. But still, there are electrons which are there in conduction band as far as conductors are concerned. But in semiconductors, there are no electrons in conduction band at 0 Kelvin. Higher energy, highest energy electrons are also in valence band only. Okay. For semiconductors, higher energy electrons are in valence band at 0 Kelvin. Okay. At 0 Kelvin, conduction band electrons are not there. Then we are going to use it, no? When we are going to use it, obviously, then temperature will be there. 0 Kelvin, who is using it? Okay. So you are bringing at room temperature, you are bringing at certain temperatures, obviously then electrons of this valence band will get energy, they will go into the conduction band and they will start conducting the current. Okay, so this basically is the energy band in any crystal. That crystal can be any element. Okay, note this one. Done? Okay. So far everything clear? Any doubt is there? Ask me. Any doubt so far? Okay, great. Right. So we understood band. What band is basically, what is energy band, what is valence band, what is conduction band. Okay. In conductors, as I told you, in conductors you have electron and conduction band also at even at 0 Kelvin. But when we talk about semiconductors and insulators, none. Even when you have the room temperature also, none of the electron go to the conduction band. Semiconductors, as you give them a temperature, they go to conduction band and start conducting. Okay, that is the difference. So, on the basis of band theory, how we differentiate conductors, insulators, and semiconductors, that we are going to see now. Okay, differentiation between conductors, semiconductors, and insulators. and insulators on the basis of band theory. Okay, what band theory says? Band theory says when you talk about a conductor, and we are talking about conductor actually, the valence band, and now here we are going to talk about only about valence band and conduction band, not the lower energy levels. Okay. So in conductors, they say that the valence band and conduction band are actually overlapped. Okay, there is no gap between conduction band and valence band. There is no gap. So that is why you don't require any energy for sending the electron for conduction. They are readily available. Okay, conduction band and valence band is overlapping, right? Something like this. If I make here conduction band, I make here valence band first. This is valence band. We'll write it as VB. Okay, and here is conduction band. Okay, this is conduction band, and you see that this is overlapping region. This is overlapping. Overlapping region. So actually, the lower energy level of conduction band and the higher energy level of valence band, okay, they are one into other one. Okay, this is what? Lower energy level of CB. This is CB, okay? 1 minute. This is conduction band and this is valence band. Okay, so lower energy level of conduction band is this, right? And higher energy level of valence band is which one? This. So it means you don't have to give any energy, they will be readily going into the conduction band. Okay, and they can conduct the electricity, right? This is conductors. Insulators, let's. This is for insulator we are making now. Okay, so here is valence band. Right? Then conduction band. This is conduction band. So clearly you can see that there is the gap. There is a gap between lower level of conduction band, okay, energy, not lower level of conduction band means energy I am talking. The energy here and energy here, there is a difference. Okay, and this difference we call as energy gap also you call this as, or you can call as forbidden energy gap. Okay, this is called forbidden energy gap. We write this as EG. Okay, right, this is what? EG. And what is this EG basically? The difference between lower level of conduction band and higher level of valence band. That is called forbidden energy gap. Okay, so there is a gap, but this gap is less than 3 eV in semiconductors. Okay, this gap is less than 3 eV. In fact, the two semiconductors that we are going to study, we have in our syllabus, silicon and germanium. Okay, so energy gap for silicon is in fact 1.1 eV. That I have written less than 3 eV. way less than 3 eV also. And germanium is even less. Germanium is 0.7. So very less energy gap is there between in conduction band and valence band in semiconductors. What insulators? Insulators will be more than 3 eV. Okay, so gap will be more. Okay, note this one. Any doubt is there? Ask. Done? This one I think I should make with color, then it will be more clear to you. This is conduction band. Okay, and this lower one with white also, that also I'll change the colors. And this is valence band. Okay, so this is overlapping region. Right, students? Done? Shall we go ahead?
Yes, sir.
Okay. Now, insulator also is there. We can make insulator. Here itself I will make. Okay, if you have done it already, then in this one we will make for insulator. It's written already, insulator also. Okay. So what I am going to do, I am just going to increase the gap between them. Okay. So just increase the gap. Okay. We'll just take it up like this. You see that the gap has increased between valence band and conduction band. And this is forbidden energy gap, Eg. So this has become more than 3. This is insulator. Okay, so it's tough to take an electron from valence band to conduction band. Okay, if we talk in terms of like in this valence band, it will be totally filled. Okay, if the electrons are totally filled, they are engaged in covalent bonds and other things. So it will be difficult to take out or break the electron bond to take them into conduction band. Right, so those are insulators. We require very, very high energy to break the bonds and liberate the electron and send it to conduction band. It does happen. It's not that it does not happen. It does happen. but you require a lot of energy, and that's what this is showing you. Okay, note that. Okay, right, students. Then what? Types of semiconductors. Now we know that there is a band theory, there is valence band, there is conduction band. All this we know. Okay. Now there are two types of semiconductors we have. What are those? One is pure semiconductor, other one is compound semiconductor. Okay. Two types of semiconductors we have. Two types of semiconductors. One is pure semiconductor. Now, pure semiconductor means what we have in our syllabus also, silicon and germanium, right? Silicon and germanium. Compound means what? Compound also, if you read NCRT, in that one, in certain places they will give you that the compound semiconductors are better for this particular purpose. When we see applications, we'll see in a day or two. So in those ones, they have given the examples of compound semiconductors. So what compound semiconductor is? They are not like this is one element. Okay. In compound means is you have two elements involved in that. So compound semiconductors. Compound semiconductors, what you will see that this they will write it as like this: gas, gallium arsenic. Okay, gallium arsenic, and what? Indium phosphate. Less, you will not find much. This you will find more. Gallium arsenic. Okay, so these are compound semiconductors. Which one we are going to study? We are going to study pure semiconductors. We are not going to talk about these two. But in examples, you will find it. Okay, so these are also semiconductors only. Only this is like two elements are mixed in that. Okay, indium phosphate and gallium arsenic. Okay, note that one also. Come on, fast. Done. Completed, students. Okay. Now, since we have decided we are going to talk about silicon and germanium only, then in this one also we can classify them into two types: intrinsic semiconductor and extrinsic semiconductor. Okay. Intrinsic semiconductors and extrinsic semiconductor. Okay, intrinsic is again called pure. Intrinsic is called pure semiconductor. We are not going to mix anything. Extrinsic is we slightly some doping we do. Some doping, like in compound semiconductors, was not doping. Okay, I literally mix two crystals in that. Here it's like a little bit of doping you are doing. In what? In extrinsic. Small, any other thing we are adding in that one. Just like you have a certain amount of water in that one, you mix sugar or you mix salt in that. That's called doping. That we'll do in extrinsic semiconductor. We'll call it as impure semiconductor. Intrinsic is called pure semiconductor. Okay. So first is intrinsic. Intrinsic semiconductor or pure semiconductor. Okay. So now when we have decided we are going to discuss, how much time is there? I think 3 minutes are there. So let's discuss it. I'm not writing anything. Let's discuss. Okay. So intrinsic or pure semiconductor, when we have decided that, and we are going to discuss about silicon and germanium. Silicon and germanium both have 4 electron in valence band. Okay, 4 electrons in valence band. So we can say that valency is 4, right? So these 4 electrons will try to make what? Will try to engage with the other atoms of the same germanium so that they can make their octave, right? So if suppose I am talking about germanium, okay, these have 4 electrons. Okay, now what it will make, here is also germanium, because we are talking about pure semiconductor, right? So this side also will be germanium, this side also germanium. Very similar to carbon, right? Carbon also has 4 valency, no? Correct or not? Carbon also has 4 valency. Okay, so here 4, so here 4 are there. Here also 4. Here also. Here also. So engaged here. Okay. Engaged. Engaged here. Engaged here. So neighboring 4 atoms. Okay. It will take the assistance in making its octave. So they may form what? Covalent bonds are here. Okay. So these covalent bonds are there. They are making their octave and they are very happy. But do we want this? We don't want this. We want them to conduct. At the moment they are not conducting. They are all in valence band only. They made their octave completed. Right? So they are not going to conduct the electricity for us because in conduction band there is no electron. So what we do? We heat them. In any ways, you can make light to fall on this one. Okay. Or you can heat them. Or you can put electric field. It's your wish how you are agitating. So what will happen? Some of the bonds will break. Some of the bonds will break. And since you have given energy, so electron have got energy. So they will jump to conduction band. Okay, they will go to conduction band. So when they will go to conduction band, you will be having certain electrons to conduct the electricity. Yes. But at the same time, there is vacancy created here. If suppose this electron is gone, so here is a vacancy created, and this vacancy is called hole. What the word given to here, that is here hole. Okay, now because hole is created in this, here also current we get. How? Because higher energy electron will jump into the vacancy created. Okay, suppose there is the vacancy created in L shell. So what will happen? From M shell one electron will jump. Then to fill it, and from N shell one electron will come. So there is a motion of hole. Actually, electron is jumping, but we see it as the hole is moving. So there is motion of hole in valence band, and there is electron which is already going in conduction band, that is also moving. So we get current because of electron in conduction band as well as hole in valence band. Okay, this is how we get current in intrinsic semiconductor. So we are finishing today here only. Okay, the next class we will study more about it. So today's class, is everything clear to you students? Any doubt? All right. Okay students, then